All right, let's just jump right into it. I want you to picture this. It's 1943. The world is literally tearing itself apart. And right in the middle of all that, two researchers publish this paper that does something just mind-blowing. They propose a mathematical language for the brain itself, a paper that would, without even knowing it at the time, invent the core idea of artificial intelligence. And it all boils down to this one single explosive idea. That the firing of a neuron, that little zap of electricity, isn't just some random biological noise. No, they said it's a proposition. It's a statement that is either true or false. It's pure logic. And that one idea, it just blows up into this massive question that we are still wrestling with today. What if that incredibly complex, mysterious thing we call thinking is, at its heart, just computation? Just a series of logical steps running on that 3-pound computer we all have inside our skulls? Well, that's exactly what we're going to unpack. So let's start with what this paper was really trying to do: build a formal logic for the brain. McCulloch and Pitts weren't just poking around at biology. They were trying to write the source code for thought itself. They were treating the brain like a machine that could be understood. What's absolutely wild is when this happened. This was before the first modern computers were really a thing, way before the transistor was even invented. And yet here they are, laying out the theoretical blueprint for both AI and computational neuroscience. It was just a radical, incredible leap of imagination. So how do you even start to build a logic for something as messy, as beautifully complex as the brain? Well, you start by simplifying things. McCulloch and Pitts laid out a few fundamental assumptions, kind of like a basic operating system for their ideal neuron. Let's check out those rules. The whole thing is built on this one single principle: all or none. A neuron doesn't fire a little bit or kind of fire a lot. Nope, it's binary. It's either a 1 or a 0. On or off, true or false. This is the crucial connection that lets them bridge the gap between mushy biology and the clean, crisp world of logic. And from that simple on or off idea, they built this elegant little rule book. Rule 1, a neuron is either on or it's off. Simple. Rule 2, to flip it to on, it's got to get enough go signals, what they call excitatory inputs, to push it over a certain threshold. And finally, rule 3, just one single stop signal, an inhibitory input, can act like a veto, shutting the whole thing down no matter what. That's it. Simple rules, but as we're about to see, they have some seriously powerful consequences. And this is where the real magic happens. This is the aha moment of the whole paper. McCulloch and Pitts showed that if you take these simple, rule-following neurons and you just wire them together in clever ways, you can build circuits that do real, actual logic. Okay, so let's take a basic logical idea, or. The statement A or B is true if A is true, or if B is true, or if they both are. The paper said, hey, we can build that with neurons. You could have a third neuron, we'll call it neuron C, that fires if it gets a poke from neuron A or from neuron B. And this diagram, which is based right on the paper, shows exactly how it works. See, we've got two inputs, N1 and N2, and they're both connected to our output neuron, N3. Now, the key is that the threshold for N3 to fire is just 1. So if N1 fires, that's enough. N3 fires. If N2 fires, N3 fires. Bam, you've got a biological OR gate. Okay, so that was OR. What about something a little stricter, like AND? The statement A and B is only true if and only if both A and B are true at the exact same time. And yeah, you guessed it, the paper showed how you could wire up a circuit for that too. And the secret is right here. Look at the threshold of our output neuron, N3. It's 2 now. What does that mean? It means one little input signal just isn't going to cut it. It needs a signal from N1 and N2, both arriving together to have enough juice to fire. And just like that, you've created a biological AND gate. With just these building blocks, you could, in theory, build any logical expression you can dream of. Okay, logic gates are cool and all, but thinking is so much more than that, right? It's about time. It's about memory. A simple circuit just takes an input and spits out an output. So how does the brain actually hold on to information? Well, McCulloch and Pitts had a really elegant idea for this too. So let's look at two kinds of networks. On the one hand, you have a feed-forward net. Information just flows in one direction, kind of like a river. Input, process, output. It's simple, but it has zero memory of what just happened. But then you have what the paper famously called a net with circles. And here the output of a neuron can actually loop back and become its own input. That feedback loop, that's everything. And here's the beautiful part of that design. Once a signal gets into one of these loops, it can just keep going around and around, reverberating, echoing, long after the original trigger is gone. The network is literally sustaining its own activity. And by doing that, it's holding on to a piece of information over time. It's a memory, created from nothing more than the wiring of the circuit. It's incredible. So, if neurons can do logic, and their circuits can create memory, what does that actually mean for how we understand the mind itself? This is where we zoom out and look at the big picture, the profound and just massive legacy of this one paper. The impact was, and I am not exaggerating, staggering. This paper was the first to draw a clear line between the biology of the brain and Alan Turing's theoretical universal computer. It became the literal blueprint for artificial neural networks, which is the foundation of all modern AI, and it gave fields like psychology and neuroscience a powerful new language to work with, the language of computation. Which brings us to what might be the paper's most powerful message, and you can feel it in this quote from their conclusion. Their goal was to pull the mind out of the shadows, to take it from being this ghostly, mystical thing and to ground it firmly in science. They were arguing that our thoughts, our feelings, even our problems, are at their very core the products of a physical, understandable, logical machine. And that, of course, leaves us with one final absolutely massive question. If our brains are just machines, logical nets following the rules of computation, what does that mean for us? For our sense of who we are, our choices, what we call free will? The paper doesn't give us an answer. It just cracks open the door and leaves us all to think about the consequences of its brilliant and maybe a little unsettling idea.